61A, Lecture 15, Q&A.
So the question was, what does it mean to reference a list? And in the last video, there were a bunch of examples of different expressions that evaluate to the same list. And each way of evaluating you can think of as a reference. So this notice of a reference is I can refer to Hani as Hani, or professor of CS61A, or coolest guy I know. And these are all like different ways of referring to the same thing. And so different references. And the same story holds for any object in Python, but it's really important for lists because lists change. And so if you have multiple references to the same list and that list changes, then the value that you'll see when you evaluate any of those expressions that refer to that list is going to change as well. So we see this in simple examples and moderately complicated examples and really complicated examples. So maybe we'll start with a moderately complicated one, and then we'll decide whether we should go simpler or more complicated. So if you have a list, one with another list in it, 2, 3, and then you have B equals A and C equals A1. And then you append 4 to C. This will actually change B. And let's see why. So if we print B, we won't get 1, 2, 3, but instead 1, 2, 3, 4. In this case, A and B are both references to the same list. It's this list, this box, which happens to have as its contents 1 and another list 2, 3. C is a reference or a name for the element at index 1 of A, which is also the same as the element at index 1 of B, because A and B are just two different names for the same thing. And that means if I append to C, I've really changed A and B as well, even though my expression says C.append 4. Anything that contains this value of C is going to be affected as well. So when we print B, we'll see 1, 2, 3, 4, as opposed to the original 1, 2, 3 that we typed in, because we mutated or changed part of it.
So let me just inject something here. So the most important line here is the B equals A line, right? So that before we were doing lists, if I had said, for example, A equals 5 and B equals 6, if I changed A, B doesn't change. Yeah. So that's sort of what's a little confusing here. But with lists and with objects, when you assign one variable to another variable, each of which are now lists, there's only one copy of the data. Yeah, that's the important part. But when I say A equals 5, B equals A, there's sort of 2 5s out there in space. And this is what's nice about these environment diagrams. So right after and you can see it here in the environment diagram, B is not pointing to its own list. It's pointing, there's only one list in memory now. Both A and B are pointing to it. And now I can modify, this is sort of what's sort of terrifying and interesting about it, is either if A modifies, it modifies B. If B modifies, it modifies A. There's only one list in memory. And that's the thing to keep in mind when you do what's on line 2, is you're not making a copy of the list.
Great question. So the question is about this example from lecture that involved printing out T and seeing some dots. Let's see if we can find them. Oh, there they are. What is that? Well, let me give you kind of a simpler example that doesn't involve slice assignment, just so I make sure everyone can follow along. So I'm just going to comment those out and make a new T, which is a list containing 1, and then I'll append T to it. Like, what should this look like? This should be a list that has 1, and then within it, it has a list that has 1, and within it, it has a list that has 1, and within it, it has a list that has 1, and within it, it has a list that has, and this could go on for, a little while. What's interesting is that there is some logic built into Python about how values are displayed. So for example, the fact that a list appears with just one space after the comma is part of how Python works. Now, that part about how Python works is actually just a function that says whenever it's time to display a list, you should display it in this particular way. And that function has the following behavior. If at any time you want to display the entire list that you're in the process of displaying, then don't display it, but instead display this ... to say, this would kind of go on forever because T contains itself, but we don't want to fill your screen with ones, and so we'll stop there. So yeah, I guess we'll study this in more depth later in the course, but one of the interesting things is that there's a relationship between this object, which is weirdly self-referential, and the way it is displayed. And the relationship is some function that's built into Python, but we could write it ourselves if we wanted to, that takes in T and starts displaying it. Since T is a list, it has an open bracket. Since the first element is 1, it writes 1. Since there's another element, it writes the comma and the space. And then since the next element is T again, it has this special case where it says, okay, time to draw a list, but not display its contents because that would take forever. So maybe we'll then go back to this particularly bizarre thing you can do in Python, which is slice assignment. So slice assignment basically says, take a piece of the list, there's the slice from 1 to 3, and replace it with the contents of another list. So I could replace it with 5, 6, 7, and then the 2 and the 3 would go away, and the 5, 6, 7 would be there, and I would get 1, 5, 6, 7. If instead you replace it with something that has a T in it, then you get that ... But I mean, this could have been 5, 6, 7, and then T, and then the ... would appear at the end.
By the way, notice too that, I mean, John said it exactly right, that there's a distinction between how the data is being stored and how the data is being printed. So in the print, it looks like the list goes on forever, but in storage, it doesn't, because that last element is just a pointer back. So it's not like we blew out memory having to store this huge list. It's not until you go to print this thing that you have to be like, oh, what's that last element? Oh, it's the first list. Oh, what's the last element of that? And now you have sort of a problem. But from a storage capacity, from a representation capacity, no problem at all. I just have a self-referential, and somebody asked in the question, can you think of this as sort of recursion? You can think of sort of like you're defining the list in terms of yourself.
Yeah, exactly. The list is recursive in the sense that it contains itself. Also, the function that prints out a list is recursive in the sense that what it does is it prints some brackets and then it displays all of the elements. And so to display the whole thing, you display each of the elements. That sounds like recursion to me. And it happens to have this base case, which says if it's ever time to display the whole thing again, just return this special ... thing instead of continuing.
All right, great. Sounds good.
Somebody's asking in the chat, what kind of situation would this kind of self-reference be applied? Well, that's a good question.
Yeah, so if you wanted to represent a website where the website is like a list of the things it links to, sometimes websites link to themselves. And so if you want to simulate the idea of clicking on that link 9 times, which kind of just cycles back to itself over and over again, well, you could do that using a Python list. So there are things in the world that refer to themselves. That's why you would use this. I don't see like another good reason why you'd use this, though maybe there is, but I think that's the main one.
Yeah. And there's another question, is the ... because of an quote unquote infinite loop that calls T or because it calls itself? Yeah, it is essentially an infinite loop. You can think about it like that.
Exactly. So I would say the function that displays the list would loop infinitely if it weren't for the fact that we had this special case, and that would be bad. So the object itself is finite. Like it refers to itself, but it's really just a list with 1, 2, 3, 4, 5 elements. Yeah. But displaying it could take forever if you're not careful.
So there's that it's a really interesting distinction. I can have something that is finite, but that takes an infinite amount of time to display because it's self-referential. That's fine, right? It's like chasing your tail.
Yeah, and it's like, well, Well, okay, so this shows up in mathematics sometimes. I guess we're going too far astray. But you could define a sequence of numbers, like it starts with 0, and then 1, and then each element is the sum of the previous 2, is the Fibonacci sequence. That description was finite, yet the sequence is infinite if I wanted to write it out. That's kind of what's going on here.
Nice. Very nice.
Good question. So the question is, what's the relationship between a selector function in data abstraction versus a dot expression that refers to an attribute of an object in object-oriented programming, which is kind of what we're building up to? And the answer is there's no difference. So in a typical program, you wouldn't have both. You kind of pick how you're going to do things. The selector function was there to show you that through data abstraction, you could bundle stuff together and break it apart using a constructor and selector functions. And this functionality doesn't actually require you to define your own functions. It's built into Python. And we're seeing that for the first time with the objects video today, is that lots of different values are, in fact, abstractions that have their own components. And those components in the object system are called attributes. You access them through dot notation. And so like in a typical Python program, you don't write a lot of constructors and selectors. Instead, you write a bunch of dot expressions that access particular attributes. And that's fine. Python could have been built another way. And it is built with a constructor for lists, where like you can build a list out of something like a tuple. So that looks basically like the constructors that we had in data abstraction. But instead of having just a bunch of functions to access the elements of this value, the way Python is built internally is that you access the components, not through selector functions, but through dot expressions that get particular characteristics. Like, I guess there's this, like for lists, there's this special syntax where you use square brackets. But for a lot of different things, I guess I should have talked about dates. With dates, you use dot expressions to access the parts. So same concept, two different ways of doing it. You could roll your own, which is to define functions, so selector functions and constructor functions. Or you can use the built-in functionality within Python in order to use attributes and access them through dot expression. And you're basically doing the same thing with slightly different code.
Yeah, it's important to understand that that square bracket notation is a selector. It's just a syntactically different selector, right? So all of these, it's sort of like using the plus sign as opposed to the add function. Same thing. It's just a different syntax that's just a little bit more convenient because we use it so often.
So great question. The question is about how slice assignment works, which is the weirdest thing in Python. Maybe we shouldn't even teach it in this course, but I did, so now we'll learn about it. It's called slice assignment because we have a slice and an assignment statement. And this has its own behavior. It's not like you can think about this as you're like first computing the slice and then you're assigning to it. Instead, this whole thing is kind of its own construction. And so it has its unique behavior that you have to learn, and it's different from how all other assignment works. The way that this works is that this must be something you can slice, like a list, and something you can change, well, like a list. This must have elements. So if, for example, I put 5 here, I would run into an error. It would say, can only assign an iterable. That's the problem, is that 5 is here, and that's not allowed. In slice assignment, it must be the case that you have something that's got elements in it, like a list or a tuple or a string or whatever. Now, what it does, so we kind of have gotten the domain right. We know that this needs to be something that we can slice, and we need to decide how we're slicing it, and we need some elements to insert. Now we have to talk about the behavior. And the behavior is that S gets modified. The way it gets modified is that whatever slice here is removed from S. And then at the position that that slice was removed, all of the elements of this are inserted into S. So S actually doesn't have any elements from 0 to 0 because this is a 0 length slice. It does have a position. It's like right here before the 1. But it doesn't include the 1 or the 2 or the 3 because it only goes from 0 to 0. So If, for example, I had just taken a slice from 0 to 0, I would get an empty list because there aren't any elements from the slice from 0 to 0. But that's not what we're doing. We're assigning to this slice, and we're assigning some new elements, which means we're going to insert into S all of the elements in T, which is 4 and 5 and 6, and we're going to put them in a particular position, which happens to be at the beginning. So we get 4, 5, and 6 at the beginning. If instead I had sliced from 1 to 1, that's still a 0-length slice, but it's in a different place. So the 4, 5, 6 would have shown up starting at position 1, which is where this empty slice would have been. It would have been like right in there. And so that's where we put the 4, 5, 6. If we had had a non-empty slice, the slice from position 1 to position 2 covers the 2. This would remove the 2 and replace it with the 4, 5, 6. So we get 1, 4, 5, 6, 3. I think the reason this exists is that Python tries to do this quite efficiently. So if you went through and removed all these elements and then you started inserting afterwards, then sometimes that would be a little bit slower than kind of doing it all at once, which is to remove the slice and slap in some replacement values instead. But it does mean it's like one more piece of syntax that you might want to know. And since we taught in the course, I guess you need to know it. Although this is definitely not the most important thing you're supposed to learn from this lecture. It just happens to be one more way that you can change the contents of a list. Good question. So why isn't it that T becomes an element of S? And the reason is that's just how slice assignment works, is that it takes a container full of elements and it doesn't put that whole container in S. Instead, it puts the elements of that container in S. Now, it doesn't necessarily copy those over. If, for example, T had lists in it, so T has a list in it, then the things I'm going to do is I'm going to remove the 2, because that's the slice from 1 to 2. You can see the indices here. And I'm going to replace it with the number 4, this list, and the number 6. So what we'd end up with is 1, 4, this list, the number 6, and the number 3, which was in there before. A question of the chat was can you explain why you cannot insert an integer into a list again? In general, you can insert integers into lists if you're using something other than slice assignment. So if I were just using element assignment, then I could put the number 5 in there, or let's pick another number, the number 8 in there, no problem. And it would just change element number 1 of S to 8. That's okay. The reason that we ran into a problem is that we were using slice assignment, which is this weird thing that takes multiple elements from S and replaces them with the elements from 8. Oh, except 8 doesn't have any elements. That's why we ran into a problem here, is that slice assignment only works if what's to the right-hand side evaluates to something that has elements in it, like a list. So I could have put 9, 10 in here, or I could have put T. Both of those are lists. And then what it does is it replaces what was in there before in this slice from 1 to 3 with these new elements 9, 10. But it actually doesn't put a list containing 9 and 10 in there. It puts the elements themselves.
And Steve's asking, why did you use S0:0 instead of S0:1? The difference is the S of 0:0 is not replacing any elements. It's inserting at position 0. The S0:1 is going to replace what's in the 0th position with whatever's on the right-hand side. So he could have done that. So it's a question of insertion versus replacement.
Yeah, so the second version lost the 1.
And
Okay.
Michael's asking, is S0 the same as S0:0? Yes and no. So if you say S0 is equal to something, then you are not using that slice assignment operator. So it's different. Then you're allowed to have whatever you want on the right-hand side. Yeah. So distinguish between list assignment with a simple index and the slicing assignment, as John said earlier on, is a thing in and of itself. It is distinct from other types of assignments.
Yeah, let's just try to get these two things next to each other because they do have different pictures and the differences in the pictures is important, but it's hard to keep a track of it all at the same time. So slice assignment took all the elements in T and stuck them in S. So now S, which used to have 3 elements, has 6 elements. Why 6? Well, it had 3, and we put 3 more in it. This, which is not slice assignment, but instead element assignment, just replaced whatever was in position 0 of S with a reference to T. And so we lost the 1. Remember, in this one, we didn't lose the 1. But here we lost the 1 because we replaced the 1 with a reference to T. There's no 4s and 6s in here anymore. There's only T. And this used to be 3 elements long. It's still 3 elements long. Element assignment never changes the length of the list. It just changes what's in it. Slice assignment is different. It changes the length of the list. It replaces an existing slice with some new elements.
Audrey's asking, when we do the list slicing, does the iterable that we are setting the list slice to need to be the same length, longer, or can it be shorter than the existing list slice? It can be anything you want. So the iterable, and the slice can be 0, you're inserting. It could be of length 1, 2, 3, or anything you want. And what you're going to do is think about it this way. So on the left-hand side with the slicing, you say, grab those elements, throw them out. And then take whatever's on the right-hand side and shove them into the position. So they can be longer, shorter, it doesn't matter.
And something that does show up once in a while is that you'll have some long list and you realize, oh, I don't want some of those elements. So you might slice them out, which would mean finding the slice you want from element 2 to element 5, let's say. So that's the 3, the 5, and the 6. And we could assign that to the empty list, meaning take those elements out and replace them with nothing, and then they're gone.
So that's the most common use that I use for the slice assignment operator, is to just annihilate things from a list. That's actually not that uncommon to do something like that.
The next question was, what's the difference between a tuple and a list, and what does it mean for one to be mutable and one to be immutable? And there's kind of an underlying question of what's the point of all this?
The unspoken question is, why do I care? Well, shit, man, I don't know how to answer that.
Okay, so if I call tuple on S, which is a list, you know it's a list because it has square brackets. This says, give me a tuple with the same elements as S. So now we've got 2 different objects. One's a list, one's a tuple. They got the same thing in it, but they have slightly different behavior. And the right way to think about a tuple is it's like a list, except for it doesn't allow you to do a bunch of things that you would otherwise like to do. Slice assignment on a tuple, not allowed. So you don't have to know how it works because you can't do it anyway. Element assignment, not allowed. Appending, not allowed. Extending, not allowed. You can't change the content, like the length or which elements are in a tuple. So there's nothing I can write that would take this tuple and change this 3 to a 9, or change it to a reference to this list or something like that. It cannot be changed. I could do a lot of things anyway. Like I could reassign T to something else. So I could say U equals T and T equals 9. And for this reason, it's not the name T that can never be changed. It's the tuple itself that can never be changed. The important consequence of this is that if I say U equals T, and then I write some expression involving T, it will not affect U.
Unlike a list, right? Look at the distinction here. If those were lists, it would have modified the list.
Exactly. But since this is a tuple, can't be modified. No matter what I do to T that's allowed, which a lot of things aren't allowed. You can't append, you can't slice assign, you can't element assign or whatever. But you can do some other stuff. You can take slices or whatever. Won't affect T. So if I slice this from element 3 to element 6, that is allowed. And I could call that V, but that hasn't changed U. U is still 1, 2, 3, 4. Oh, sorry, 1, 2, 3, 5, 6, 7. I don't know what happened to 4 along the way, but oh well. That's the difference, is that, a list you can do a lot of different things with. You can slice it, you can get elements, but you can also change it. Tuple, you can't do some of those things, but you can do others. You can still slice it. You can still figure out its length. You can still build a new one, but you can't change it in any way. That's what makes it immutable, whereas a list is called mutable, meaning mutation applies, meaning you can change it. But now I guess we should say something about why.
Yeah.
And I guess there's really two reasons. One is a little bit about efficiency. Sometimes a program will just run faster if it's using a bunch of tuples instead of a bunch of lists, because they can take a little bit less space in the memory of the computer. But the more common reason is that people are designing their programs so that they don't have to think about mutation. Back when you could just describe every function by its domain, range, and behavior, life was easier. I'm not saying it was easy. There were plenty of like tricky recursion problems and stuff like that. But at least you knew that if you called a function, the only thing you really had to worry about is what does it return, not what does it change. And if you use tuples everywhere, since they can't be changed, you kind of don't have to think about what does it change. You just have to think about what it returns. Whereas if you're using lists everywhere, if you're not careful, the consequence of calling a function will be not only that it changes something or that it returns something, but also that it changes something. And that's like twice as many things to keep track of when you're writing a big program and trying to understand how all the parts work. So that's like the main reason to have some immutable version of a sequence, is just to like make sure you write programs in such a way that nothing can change anything else except by passing in arguments and returning them.
It's called side effects. The thing that's scary when you call a function is there's some side effect that goes beyond just what was passed and what was returned. It modified a list, and how do I know how do I control that? And so the tuples are nice, or tuples. Which one do you call it, John? I want to call it the other one.
I've been calling it tuples all the time, so you got to use tuple for a while.
All right, I'll use
Then
tuple.
we'll switch in a couple minutes. Okay.
All right, good. So the tuples are nice because it's essentially like you're locking your data, right? It's giving you data security. Yeah.
A follow-up in the chat was, what happens if my tuple has a list in it? So this tuple is immutable in the sense that it will always be length 3, and it will always have this particular list in it. So the aspect of this that's immutable is that it will always have 3 elements, and they always will be the number 1, this list, and the number 7. Those facts cannot be changed. However, this list might change, and the fact that it is part of a tuple will not control what's allowed. It's still a list. You can still do whatever you want to it. So if I give it a name, I say T is S1, and then I start mucking around with it. I append 5. We've been, okay, I was about to do slice assignment, but I think we've done that to death today. Okay, then now, in a sense, the contents of this tuple has changed. The tuple itself has not changed. It's still 1, this list, and 7. But if you were to print it out, you'd see something different than you did before, because you'd see 1, 3, 4, 5, 7 instead of 1, 3, 4, 7. So being immutable doesn't mean that nothing about you can ever be altered. It just means that this particular part of the environment diagram never will change. Yeah, good question. So when is a value protected from mutation? There is not a mechanism in Python to take a mutable value and protect it from mutation somehow. Mm-hmm. If a value can be changed, then anything that can access that value can change it. That's just a fact about how Python's designed. This is not true of other programming languages. There are programming languages that keep track of for each function that can reference a value. Is it allowed to change it, or is it not allowed to change it? C++ is a good example of this. And that is like another element that you could add to a programming language to give yourself kind of more control over whether something can be mutated or not. But that's not something that Python allows. Instead, it's part of the value to say this value is something that can be changed, or this value is something that cannot be changed. And so lists can be changed, tuples cannot. So what about writing Python? How do you make sure that you don't accidentally change something? Well, if you have a list, there are actually only so many ways that you can change it. You can use element assignment or slice assignment. That will change it. You can use one of the mutation methods like append or extend. That will change it. If you don't use any of those, then you're not going to change it. So for example, if you just slice it, that doesn't change it. Why not? Because we don't have an equals here. If we don't have an equals, we just have like t equals this. This doesn't change s. This just builds some new list with some of the elements of s. So as long as you're not doing element assignment or slice assignment or appending or extending or removing or popping or all these other methods that perform mutation, then s will not change. And so that's the mechanism that you have to verify that you're not going to muck with something that you don't want to muck with, is that you don't use any of these. Now, to kind of be extra careful, a lot of times what people will do is they just won't use s at all because they want to make sure they don't change s. So they're not going to use s. They could instead make a copy of s. This is really building a new list with all the elements of s. And then they write all their code about t. The nice thing about this is that if you accidentally change t, you haven't changed s. So that's like a sort of heuristic mechanism for trying to guard against accidental mutation, is that you could try to avoid using this list at all, but instead use some other list. But that isn't like not really any kind of guarantee that it's impossible to mutate s. It's just a way of avoiding it.
The next question was, if you have two lists, s and t, and you append s to t and then change s, does that affect t? And if so, how?
I think the answer is that it would. If t is 4, 5, 6, and then you append s to t, now t is 4, 5, 6, followed by the list 1, 2, 3. But this is a list that can be changed, and whenever it's changed, then all of the ways of referring to it are changed as well, including looking at t's element at index 3. And so if you print out t at this point, you'll get 4, 5, 6, followed by the list 1, 2, 3, 4, because you changed this list that's in it. Okay, so the question is, do you ever have a function f of x that takes some optional second argument that is something mutable? And is this ever like a good idea? My take is the answer is no, this is never a good idea. But I have seen people use it before. They could, for example, try to write a function that returns the sum of everything f has ever been called on. So we're gonna, I guess we don't need to print. We're gonna call f on 2, then we're gonna call f on 1, then we're gonna call f on 3, then we're gonna call f on 5, then we're gonna call f on 7. This first call is gonna return 1. This second call is gonna return 4. This third call is gonna return 4 plus 5 is 9. This last call is going to return 16. You know, don't do this, but I've seen it done, so I guess you might as well know that someone else might do it. What's going on here is that we're using the default argument's value as some kind of persistent storage that's part of this function that's kind of keeping track of everything that this has ever been called on. The reason this is extra weird is that you could call f on, you know, some new thing, and then it wouldn't behave the way that you wanted it to behave at all. Like instead of summing 1, 3, 5, 7, and 9, it would sum 9 and 1 is 10, which just like is inconsistent with everything that's happened before. So
this is a nasty, nasty feature of Python, by the way. I think it's ridiculous that it works this way.
Yeah, so this is something to avoid by knowing it exists, as opposed to something to exploit or use by knowing it exists, is that the default argument value is part of the function, which means there's kind of only one of them. And so if you wanted to mess with it, you could, but don't.
One quick question, we'll get to the last hand raised. The question is the default value in a function defined in the global frame? I don't know if it's actually defined in the global frame, but it effectively is, that's what it's doing.
It is true that this expression here is evaluated in the global frame. I shouldn't use X, I should use something else. Because this is evaluated when the function is created, not when it's called. Okay, so like none of this would work anymore, but we could like return y of x or something like that. And could we refer to something globally? I think the answer is yes. See if I'm right. Yeah, so when you create the function, before you ever call it, we never called it, it not only creates the function, but it creates the default argument value, which means evaluating this expression. If this expression is 2 square brackets, that makes an empty list. If this expression is some lambda, then it creates a function.
Yeah, I don't like it. Don't do that. So the question is, what is the difference between a class and an object? The class is, here's how I think about it. Think about a blueprint for a house is the class, and the house is the thing you build from the blueprint. Okay, so I can have a class date. That is the sort of the definition of the data I'm storing and the functionality of it. And then I can instantiate, I can create as many of those objects as I want. So they're essentially realizations of the thing that you've created. So the class is just, it's sort of like a definition. Nothing exists. And then when you create an object, well, now I can sort of do things with it. So there's a class of type list, and then I can define lists. I can define 1 list, 2 lists, 50 lists, whatever I want. Yeah.
Yeah, and that analogy is nice because you can live in a house, but you can't live in a blueprint.
Right.
Like if you just have the class, you can't really do anything with it until you construct one of the things that it describes, build the house, and then you can go live in it.
Then you can go live in it, right? And it's sort of like a function definition, right? You define a function, but it doesn't do anything. It's just a definition. It just hangs out in the global frame somewhere. But then when you call it, now we're actually doing something.
And you're not supposed to know this all. I mean, it's fine that you know it, but we will cover this fact of the relationship between classes and objects next week. So it's for those of you that are a little hazy on what's going on. That's because we haven't not yet in this class defined our own class or really looked at what's inside of one. But we will.
Yeah. So what's to come is we've been using the built-in classes and of things like lists and dates, but I don't think it'll surprise you that we can now start building our own classes and our own data representations and our own functionality.
I saw one more question in the chat. Let's see if we can get it. Is a range a tuple? It's kind of like a tuple, but it's not a tuple. It's a range. For the same reason that like you can make a really long range that goes from 1 to whatever that huge number is, but you kind of can't make a really huge tuple that goes all the way to this number. So tuples have an explicit representation, like all these values are sitting around in memory somewhere, whereas this is a implicit representation of a range of numbers, which may be very long, but you really just have to remember the beginning and the end in order to talk about the whole thing. So in that sense, ranges and tuples are different. Now, they have similar characteristics, which is that they're both immutable sequences. So like tuple could have anything in it. It could have lists, it could have strings. A range can only have numbers in it. But it's true of both of them that you can't do slice assignment, you can't extend or append or anything like that. You can't try to mutate them.